Three-step process to think about how to approach this. So number one, let's just do the base concept that we just did. This one is going to reflect straight away, number one. Beam number two is going to go down and back up. Okay, so beam number two is traveling how much farther than beam one? 2t. So for constructive interference, beam 2, 2t, that would be our 2t should equal our path difference. And if we want constructive interference, what should 2t be equal to? A whole lambda, right? So it could be lambda, it could be 2 lambda, etc. So we want it to be one whole wavelength. Okay? So that's the first thing, is just kind of establish what you're looking for. The second thing you need to know is that this is now entered a different medium than air. What happens to the wavelength when you enter a medium other than air? It changes, right? In fact, if we go from 1 to 1.5, what happens to that wavelength? It decreases, yeah, so it decreases. Remember, the velocity slows down, and what does frequency do? It's constant, and therefore what should wavelength do? Decrease. So anyway, that's not really step two. Step two is find lambda in the coating or the thin film. So the lambda here that the path difference we're doing is not the path difference when it's in air, because look where the difference is that we're looking at. It's in the coating. So we have to take a look at what happens, use the wavelength in the coating itself. Okay, so maybe we'll subscript this in the TF, the thin film. All right, step number 3 is you have to check for a phase change. During the reflection. So here's what sometimes happens when things reflect off other substances. And you're going to have to remember back to last year when I did some demos with the springs. Remember, sometimes I sent in a spring like this. I sent in a little pulse and it hit the wall. What happened to that spring when it hit the wall or hit the end? It inverted, right? It flipped, it inverted. And sometimes that'll happen here. When it reflects, it's going to invert. So in other words, a crest will become a trough, or a trough will become a crest. So you have to check for this, whether there's a phase change. So the way that you know is there's always a phase change when it hits a larger index of refraction. When it goes from a small index to a large index, there will be a 180-degree phase change, or flip. Okay, so let me write that. So let's do it like this. When N2 is greater than N1, then we're going to get a phase change. 180 degree, or another way you can write this is lambda over 2, phase change occurs.
Why is it lambda over?
Lambda over 2. So why is it lambda over 2? Say that louder, Greg. Okay, exactly. So, like if we go back to this other picture, like in this case, it would be destructive interference, but if we flipped, if this one got flipped upside down, then all of a sudden now it would be constructive interference. So it's off by 1/2 of a wavelength. So it's a 1/2 wavelength change. So that's what we're going to look for. So if N2, and by N2 I mean the second medium, if there is a if N2 is greater than N1, then there's a phase change. So if N1 is greater than N2, then there's no phase change.
Because it's just obstruct.
Okay? So we talked about this last year with reflections. Whenever you a wave hit a firm surface, it inverts itself. Whenever it hits kind of a softer or a less dense surface, it doesn't flip. It stays upright. And so that you can think of this as like a more optically dense region. And so when you go from 1 to 1.5, it's going to flip. What about when you go from 1.5 to 133?
Stays up.
Then there is no phase change. So this will stay up. It won't change. All right? So let's go ahead and solve this problem then. So now we're going to take that into account when we try to solve this problem. All right, so let's find the wavelength first. So find the wavelength. And where are we going to find it? We're going to find it in air, we're going to find it in coating, we're going to find it in water. Coating. So this is the region that we're looking for. Did anyone derive the shortcut? Nobody bothered to derive it? All right, we'll do it the long way. V equals F lambda.
We try to figure it out. Got it.
What was it? 632. What did I give you? 400? Do it the long way. All right, well, she can use it. We'll have to do it the long way. Okay, someone give me the frequency in the coating, or in the air, sorry. I guess I can do it. 7.5 times 10 to the 14. Did I do that right? Okay, so that's going to be our frequency in the coating. In the air, that's also the frequency in the coating as well. Because what's true about the frequency? Doesn't change. Let's try and find the velocity in the coating. So we'll go V equals C over N. What was it, 1.5?
Yes.
So that's just 2 times 10 to the 8th. And then lastly, let's find the wavelength. Okay, what's the wavelength here?
266.
Okay, there we go. That's the wavelength in the thin film or in the coating. Okay, all right, so now we're going to just go ahead and find the thickness. So here's what you have to do. Let's go back to our picture, and we already talked about this, but let's just look at where we'll check for phase changes. So boundary 1, is there going to be a phase change between 1 and 1.5? Yes.
Well, I'm just asking, so is that supposed to be straight up and down?
Yes.
Okay.
So boundary 1, the phase change, there is a phase change because we went from a small index to a large index. What about boundary 2?
No.
No, because we went from a large to a small. So what is the net phase change? A half of a wavelength or 180. Okay? So here's how we're going to take this into account when we actually do it. So there, we'll say there is a lambda over 2 phase change. Okay, so we measure this out. We're going to go, there's multiple ways to do it. The way I usually do it is this. I'll go 2 times the thickness plus the net phase change. Phase change net equals whatever it happens to equal. So in this case, we wanted what? Constructive interference. So what should this equal? 1 whole wavelength for constructive interference. If I ask for destructive interference, this would be a half. So we just calculated the net phase change was lambda over 2. So we're going to go 2t plus lambda over 2 should equal lambda. 2t therefore now equals what? Subtract that. Lambda over 2. And the thickness is lambda over 4. Oftentimes this will be a variable only question they might ask you, so that would be, for this particular problem, that would be the answer. But we actually have a number here for this, right? Now which wavelength do I plug in here? 266 or 400? 266. You always plug in the wavelength in the coding. So this is going to be 266 divided by 4. 66.5 nanometers. Now is that the only coding that would work? Is that the only thickness that would work? How else could we find it? 2 lambda, right. So 2 lambda would work, 3 lambda would work, etc., etc. Right? They often ask for the minimum. So when you ask for the minimum, then that would be the minimum thickness. Okay, just a real quick question for other problems. What would happen if there was a phase change on both? So this phase changed, let's say this went 1.5, and this went to 1.8. So there's a phase change here, there's a phase change here. What's the net phase change? The net phase change would be 0. Yeah. Or you could say a wavelength. That's fine. 1 wavelength would be fine also. The concept of it is this. Okay, let's say this one is my crest, this is my trough. They're both in sync, right? If one flips, there's a phase change. Now we have crest on trough. But if they both flip, then what happened? What's the net change? The net change is no net change. So they're both in the same direction. So you would just say the net phase change is 0. If you said 1 full wavelength, that's okay. That would work out also as well. Okay?
Why is there only one?
What's that? In the problem we just did? So in the problem we just did, there is only 1 because we went from 1 to 1.5. So there's a phase change here. But we went from 1.5 to 1.3. There was no phase change at that point. So the net phase change would be 1. This one here? Right, so there's only 1 phase change. 2 does, which one are you talking about? The original one or the one I'm just asking about?
The original problem.
Yeah, it's 1.3. Doesn't phase change if it goes to large index to small index.
But it goes from 1 to 1.5, right?
1.5 to 1.3.
No, the second doesn't it goes from? Or is the phase
This
change
is one beam.
what it reflects off?
One beam reflects and refracts. And then this same beam, this is still the original beam, reflects here. Phase changes on the first one, but not on the second one.
So it's only the point that it reflects off.
Right.